So in terms of what we're going to deal with in introductory level physics, basically there are three types of quantities that we're going to need to add together. We're going to add together scalars, we're going to add together vectors, and we're going to add together something known as phasors. So for each of these, there's a difference in what matters. So for scalars, the only thing that matters is the amount. Scalars are basically numbers. They can be positive, they can be negative, they can be zero, but they're just a number. Vectors, on the other hand, you care about the amount, which with a vector we'll tend to call the magnitude, and the direction. So the fact that you may have two vectors that are exactly the same magnitude, they have the same length, the same amount, but you get a different answer when they point in the same direction versus pointing in opposite direction versus being perpendicular to each other. So when you change the direction, you change what you get for their summation. Phasors we'll deal with towards the end of the semester a little bit, and what we care about there is the amount plus the phase. So in terms of thinking about the physical quantities that we'll run across with each of these. So scalars, well, time is a scalar, right? We think about time always moving forward, but of course that forward isn't really a direction. Distance is a scalar. It's just a statement of how far something traveled. Speed is a scalar. How fast is something going? None of those by themselves care about direction. Mass is a scalar. And then some of the other things that we know with mass, well, if I take mass and divide it by volume, that gives me a density. So since volume is a scalar and mass is a scalar, density happens to be a scalar. And then the last three, or the last four, are the ones that we will really spend more of our time dealing with, which is energy. So the fundamental scalar problem that we'll deal with in introductory level physics is energy. So we can think about energy in terms of conservation of energy. We can think about energy in terms of transfers of energy. That's where work and heat come in. We can think about energy in terms of a rate of transfer. That's where power comes in. So all of these are very much tied into energy problems. And we tend to sort of lump the energy problem that we work most often in physics under the label conservation of energy. For vectors, again, there's a whole slew of things we're going to deal with that are vectors. So position, where you are, is a vector. So where your position is cares about the origin you choose, and then where you are in some x direction, y direction, and potentially z direction. Displacement is how your position's changing. Again, that's a vector. Velocity and speed, again, those seem to be the same things, but they're not. Speed doesn't care about direction. Velocity does. So your velocity, these two things relate to each other, but your velocity, the shortest way to think about it is that it cares about how your displacement is changing with respect to time, and displacement cares about how your position is changing with respect to time. So these things are fundamentally vector quantities. Acceleration cares about how your velocity is changing with respect to time. Forces are how objects push and pull on each other. Again, those are vectors. The pushes, the pulls, they all have a direction. Momentum is something that's tied up with both how an object is moving and how forces are exerted on it. So momentum is a vector quantity. Torque is the way that we'll see that you can change how things rotate, and then how they rotate is defined by their angular momentum. And then the last really big vector quantity that largely gets saved to the second semester of the course is talking about fields. So we'll focus this semester on forces, but forces and fields are intimately related in a handful of cases. And so that field problem is really what we end up spending more of our time talking about in the second semester of the course. But all these are vectors. We've got a shorter list for phasors, but basically phasors are what we're dealing with when we're dealing with waves. So what the phase difference is between two waves will tell you how much they add together or cancel out. And then interestingly enough, when you get into modern physics, quantum particles behave like waves. So quantum mechanics is also known as wave mechanics, And again, that's because phase matters in that circumstance. So this is really sort of the guts of introductory level physics, is really learning how to deal with these three types of addition problems. So vectors is the one that we care about right now. That's where we're going to start. And initially, so the first thing is we can draw a vector by drawing a arrow. It's very important that we draw the arrowhead. So this isn't just a line segment. The arrowhead tells us which way this object points, because with vectors we care about both the magnitude and the direction. So I care about how long this is drawn and in what direction it's been drawn. In terms of notation, if I put this little arrow over A, that tells me I'm talking about vector A. If I want to talk about the magnitude of vector A, there are two ways that I can denote that. I can either leave my vector A notation and put it in absolute value sign. That means the magnitude of vector A. Or I can take what is clearly a vector quantity and just drop the arrow notation. So both of these are ways that we denote the magnitude of vector A. We'll also talk about the x and y components of vector A. And so the x component of vector A is given by a sub x. The y component of vector A is given by a sub y. So these are components, and components can be positive, can be negative, can be zero. Components are really scalar quantities that we're going to multiply by a special set of vectors. All right, so when I still think about vector A here, one thing I'd like to be able to do is to describe it. And so one way to describe a vector is to report its magnitude and direction. So I might tell you that vector A has a magnitude of 12 meters. So we'll just assume this is a drawn to scale vector that measures a magnitude of 12 meters and happens to point in the positive x direction. If I have a second vector, vector B, well, vector B has a magnitude of 15 meters, so it's a little bit longer. You can see from the drawing, it's a little bit longer than what vector A is, and it points in the negative y direction. Vector C has a magnitude of 20 meters, so again, it's a little bit longer still, and it points in the direction 35 degrees above the x-axis. So we can talk about a direction of rotation. But one way to talk about that direction is just to say whether we're above the x-axis or below the x-axis. So notice again, I'm still, even though this doesn't point along a coordinate direction, I'm still giving you the direction by telling you some angle either above or below some reference point. Okay? So when you're giving directions as angles, there's really three pieces of information you need to give. How far do I need to rotate? In which direction do I need to rotate? And from what starting point do I need to rotate? Now, one of the things that we'll do, certainly in some of these vector problems, is we'll talk about coordinate directions rather than laying things out in terms of x and y. So we'll say, oh, here's a vector that points due east, or due west, or due north, or due south. Or we can make it off at some angle. And so again, here's just sort of the way cardinal directions lay out, right? North, south, east is to the right, west is to the left. And so in this case, we might, if we have a problem that's oriented this way, it might tell us that vector A has a magnitude of 12 meters and points due east. So instead of saying it points in the positive x direction, now we're saying it points due east. Vector B, we're now saying points due south. Vector C, still 35 degrees, but the way that we're giving the direction here is basically you want to read this backwards. So it's saying start pointing due east and turn it 35 degrees north. So sort of think of this as the 35 and the north go together. So 35 degrees north of a vector that was initially pointing due east. So that's the 35 degrees, OC pointed due east, and I turned it 35 degrees north of that. So this is another way that we'll end up trying to relay magnitude and direction information in terms of cardinal directions.